Hello, welcome back to 10-Minute Science, where we learn about something amazing in 10 minutes or less. However, right now I'm traveling in a spacecraft near the speed of light, and you are stationary on the planet Earth, so 10 minutes to me is probably double or triple the amount of time for you. What are we going to learn about? Today we're learning about how does speed and velocity work. Now you might say, how is that amazing? I think I already know how speed and velocity work. How is that worthy of something amazing? Well, the entire concept of Einstein's theory of relativity, special relativity, space and time and velocity and the speed of light and all of that stuff is absolutely critical for you to understand this material before we can learn the most amazing things that we've discovered as humanity, right? So we have to start at the beginning. What is velocity? What is speed? We're also going to touch on what is position and distance and displacement and all of these things, basically talking about motion. You'd be surprised how many things you can learn if you understand motion. Temperature of the air, it's all based on motion. Magnetic fields based on motion. Lots of things based on motion. So we're going to pick that apart. Now the first thing we're going to do is talk about some amazing and interesting speeds of objects. The first one we're going to talk about is the solar flare. A solar flare is when the sun spews out an energetic stream of particles towards the Earth. What would the speed be of a solar flare? Now, solar flares from the sun have a range of speeds, but just to pick an average number, a solar flare can travel away from the sun at the astonishing speed of 1,609,000 meters per second. Now, take a second to think about this number. Think about how big a meter is. A solar flare coming from the sun, 1.6 million of those meters per second. Now this is a gigantic number, so a lot of times what we'll do is we'll basically say that this is, 1,609 kilometers per second. And believe it or not, some of these solar flares are faster than this, and some of these are slower than this. All right, so what we're gonna do is step down from really fast things to really slow things. All right, after we talk about a solar flare, bullet coming out of the muzzle of a gun. The speed of a bullet is somewhere on the order of 180 to 1,500 meters per second, right? So these are the slower speed guns. These are the very high-powered rifles, 1,500 meters per second, incredibly astonishing speed. Now, when we talk about these really fast speeds, we need to talk about what do these distances really mean, because velocity is a combination of a distance unit in meters usually and a time unit in seconds. So let's take an aside and let's talk about some distances here. So we said the solar flare, 1,609,000 meters per second. So let's just refresh our memory and ask ourselves, what is the diameter of Earth? It's on the order of 12,756 kilometers. So if you look at this solar flare, when we take the meters and turn it into kilometers, 1,609 kilometers per second, that is a significant fraction of the width of the Earth every second that one of these solar flares are traveling at when they leave the sun. All right, let's do another distance comparison just to kind of calibrate ourselves with the velocity here. The diameter of the moon is approximately 3,476 kilometers. The diameter of the moon, 3,476 kilometers. Now, for the most important comparison, what is the diameter of Uranus? Because we always have to have a Uranus comparison because that calibrates everybody, right? What is the diameter of Uranus? We'll put that right here. And it's on the order of 51,118 kilometers. Now, what can we conclude from this? The diameter of the Earth being about 12,000 kilometers, the diameter of the moon being about 3,400 kilometers, the diameter of Uranus just a little over 51,000 kilometers. It means that Uranus is really, really big. Never forget that. So now that we have calibrated ourselves with distance, we return to our speed chart here. What is the speed of sound? The speed of sound, the so-called sound barrier, is about 343 meters per second. However, when we talk about the speed of sound, we will get to that a lot later. The speed of sound is the speed that a wave travels through the air medium. So it's, if you can think of a slinky or a spring expanded and you can shoot a wave and a compression wave through that medium, then that is the speed of the disturbance, the speed of the sound wave. But it depends on temperature. So this number, 343 meters per second, this is at 20 degrees Celsius dry air. And it's also specified at a certain altitude, and there's basically it depends on the density of the air and also how much water is in the air. So this is a good average number, but the speed of sound actually differs from day to day. All right, let's go take a look at the speed going down the list here, the speed of a race car. Now, there are many kinds of race cars. There's the Formula F1 race cars. There's just regular cars that are fast. You know, which one do I pick? Well, I'm going to go with the upper end of this, around 100 meters per second. So we're going down the list. 100 meters per second, pretty darn fast, but compared to a bullet or a solar flare, it's basically nothing. Now let's go down the list here. Let's talk about animals. How fast can a cheetah run? Approximately 29 meters per second. Cheetah's very, very fast. 29 meters per second, still nothing compared to these other numbers above us. Now we think humans are so advanced and so superior in a lot of ways. How fast can a human run? A measly 5 meters per second. Of course, there are faster humans and slower humans. I'm not saying this is absolute, but this is on the order of what a human can run. And just to calibrate ourselves, let's talk about a walking human. A human that's not doing anything other than a brisk walk, 1.2 meters per second. Now, we're not done with the comparison of speeds, but I just want to remind you, I've written down the units every time here. Meters per second, meters per second, meters per second, meters per second, all the way down. I occasionally switch to kilometers per second if it makes sense. But every time we talk about speed, and later in a minute we'll talk about velocity, it's always a distance unit divided by a time unit. That's built into the units. So we're going to talk later as we get into other lessons about Einstein's theory of relativity and how it's so crazy that space and time are mixed together, the space-time continuum, you know? We all heard of these things. But I'm trying to call your attention that the concept of velocity that you already know, just regular old velocity driving down the road, meters per second, it already includes a distance unit and a time unit. So our concept of velocity is already a mixture of space and time. Einstein took that to the next level, unifying it in a way that had not been done before, but the concept shouldn't be so weird to you because the concept of velocity already involves space and time. Just want to put that in the back of your mind because as we go down the road, we're going to combine space and time even closer as we get to discussing Einstein's theories in future lessons. All right? So I wanted to include this next one here because I find it fascinating. Air molecules at room temperature. How fast do you think air molecules are zooming around in the room? Now, you all know that the air is, you know, there's oxygen and nitrogen. They're colliding with each other. They're bouncing off, you know. That's what we call pressure. The collisions are causing pressure and the air pressure and things like this. But what do you think the actual speed is in between the collisions there? So when you study this, and we will study it in the future together, this is on the order of 400 meters per second. This is a number that blows a lot of people's minds. Those people have no idea that the air molecules in the air moving around are 400 meters per second. It's related to temperature. We now know, and scientists didn't know for a long, long time, that the concept of temperature was really related to the speed of the gas molecules or atoms or molecules or whatever it is. Those two concepts were different. They didn't understand that the concept of temperature was really related to the speed of the atoms and molecules until much later in physics, but now we know it to be true. So when something is at 1,000 degrees compared to something at 200 degrees, the gas at 1,000 degrees, or whatever it is, a liquid or a solid or whatever it is, those atoms and molecules are moving faster. But at room temperature, that's why I specified room temperature, the air molecules are still moving at a very blisteringly fast 400 meters per second. Now, you might be inclined to ask, well, if the gas around us is moving so fast, why can't I harness that and make an energy machine out of it? I want a free energy machine. I want to power the whole world. And if the air molecules are moving at 400 meters per second for free, so to speak, it's not really for free because the energy is coming from the sun, which is not free. But anyway, we can consider it being free energy, right? Why can't we just make a free energy machine out of the air? Well, here's the reason. Because one air molecule is moving this way, the one next door is moving that way, the one next door is moving that way, that way, that way, that way. They're all moving in different directions. They're all colliding with each other and bouncing off and moving in opposite directions constantly. So you cannot make an effective energy extraction mechanism from that, because even though they're all moving fast, they're all moving in random directions. You see, the only way that we can build machines to get useful work out of a gas is if there's some kind of temperature difference between reservoirs. We're going to talk about that later when we get to thermodynamics. But if you think about your car engine, you have to have an explosion, a high temperature thing happening inside the engine to make it go. Steam engine, you have to have a high temperature thing inside compared to the environment to allow it to go. And the same thing is true of other types of engines, nuclear reactors, anything like that. You have to have some sort of differential or some preferential flow to make it work. For instance, hydroelectric, when the river or the river is flowing through the generator, the bulk atoms of the water is moving in one direction, so you can extract energy from that, right? But in the air, they're all moving random directions. So any device you try to build to harness that, it's just going to be pushing in all random directions, and you don't have a net direction to extract energy from. Believe me, people have tried. You need some kind of gradient. And so that's the reason why, even though air is traveling so fast, we can't build a free energy machine out of it. Now we're going to the big dog in the room, the speed of light. We've done all these things and talked about speed of different things. What is the speed of light? Well, the way we're told to memorize it as students is it's about 3 times 10 to the power of 8 meters per second. But I'm going to write this number out because we need to spend a couple minutes talking about it. When we write the speed of light as 3 times 10 to the 8 meters per second, what it really is 300, and this is approximately 300, 000, meters per second. So if you put there's a 3 here, if you put the decimal point here, and then the power of 8 means you move it 1, 2, 3, 4, 5, 6, 7, 8. That's how you get this number, 300 million meters per second. Let's say it again, 300 million meters per second. That is an incredible, inconceivably huge speed. The best way I think about the speed of light is that a photon of light can circle the entire planet Earth 7 times in 1 second. Just think about that. Here's 1 second. There's another 7 times around the Earth. 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 You see what I mean? Light is really, really, really fast. Now we'll get to later lessons. Why is the speed of light the ultimate speed limit? There's a lot to talk about there. There's a whole branch of science to talk about why it's the ultimate speed limit, why nothing can go faster than the speed of light. That's not for this lesson. We will get there, I promise you. But I do want to caution or bring your attention to, even though we abbreviate it as 300 million meters per second, the real number is really equal to 299,792,458 meters per second. So you can see why we rounded up to 3 times 10 to the 8, or 300 million meters per second. Because nobody wants to write this number out, and this number is good enough for pretty much any calculation you would do, unless you're working in particle physics, in which case you have to use much more accurate numbers. All right, so the first part of this lesson is all about the speeds of everyday things around us, from the ultra-fast things like the speed of light and the solar flares, down to the slow things like humans walking around at 1.2 meters per second. So now we need to talk about the difference between speed and the concept of velocity. Now, in everyday language, we consider speed and velocity to be the same thing. I guarantee you, if you take 100 people and ask them what the difference between speed and velocity is, most people can't tell you, because in everyday language, we just consider them to be the same. I'm traveling at a speed of 5 meters per second. I'm traveling at a speed of velocity of 5 meters per second. They mean the same thing to everyday language, but in science, they don't mean the same thing. The speed, I'm going to say it verbally, and then we're going to write some things down. The speed is a class of objects known as a scalar, whereas the velocity is a class of things we talk about in science called a vector. Okay, a scalar, we have to back the truck up one more level. A scalar quantity is a number. It's just a number. That's all it is. So what we're going to do is, I'll go over here, and we're going to talk about the concept of a scalar quantity, and we're going to talk about how that compares to a vector quantity. And then we're going to circle back and tell you how speed and velocity fits into these buckets. What are some examples of scalar quantity? Temperature is a scalar quantity. Why? Because at this position where my finger is, the temperature is 34 degrees Celsius. It's a number. There's no direction. It's just a number. So temperature goes in the scalar category. Pressure Pressure is a scalar. Why? Because where my finger is, there is a pressure. It's however many pascals of pressure or however many atmospheres of pressure. There's no direction associated with it. It's just a number at this location. So scalars are just numbers. Another big one is energy. You can say how much energy exists in the magnetic field of the Earth. See, the Earth is surrounded by a magnetic field, right? But magnetic fields store energy, just like electric fields store energy. So at my finger, I can say there are X number of joules of energy stored in the magnetic field and could be released in various ways. We talk about another lesson. But that's just a number. Energy doesn't have a direction. It's not like I have so much energy units in that direction or that direction. Energy is just a number. How much potential or kinetic energy I have, and we'll talk about those concepts later. They're all scalar quantities. Now, let's talk about the concept of a vector. What is a vector? A scalar, I guess I'll put in parentheses here. It's just a number that has magnitude. M-A-G means magnitude. It just means a number, like literally 10, 5, -2, -3, a number, any kind of negative or positive number, whereas a vector has what we call magnitude and the and is very important, direction. In other words, there's a directionality to the vector, right? What are some examples of vector quantities, aside from velocity? I already gave that one away, right? Well, magnetic field. Magnetic field's a vector. Why? Because whenever you see a bar magnet, you see the lines, you can draw little arrows on the lines. There is a magnetic field at my finger that has a strength, right? And in the units of magnetic field, we'll get to later, but it also has a direction. It's pointed that way. Because the Earth's magnetic field comes out of the poles and goes back into the other pole, there's a directionality associated with the magnetic field lines, right? But just like magnetic field's a vector, electric field is also a vector, right? Because around every electron or proton, there also exists an electric field, which is an invisible lines of force, so to speak, coming and emanating from charged objects, which can push other charges around, and there's a direction associated with it, right? Here's the one that's most commonly associated with everyday life, a force. Any force is called a vector quantity. It has a magnitude, a number, along with a direction. If I push in a certain direction, I'm pushing with a strength, with a unit of force we'll talk about later. The unit of force is called a Newton, but I'm pushing that way. And so that's a vector. I'm pushing so hard in this direction, but if I turn and push this way, even if I'm pushing with the same amount of push, the same magnitude, the direction is different, and so the vectors are different. So forces are also vectors. So I've saved the best for last, right? The most important scalar quantity that we're going to talk about here in this lesson is called the speed of an object. This is a scalar quantity. And the most important vector quantity in this lesson that we're going to talk about is called the velocity. So I told you a second ago that if you were to go into a random room and grab 100 people and say, tell me the difference between speed and velocity, most people can't tell you because in everyday language they mean the same thing. Here's the answer. Speed just tells you how fast something is moving. But velocity tells you how fast it is moving and in what direction it is traveling. When I launch a rocket into space, I don't want to launch it down into the ground. That's ridiculous. I have to launch it at an angle up. That angle specifies the direction of the motion. The direction of the vector velocity is just as important as how much speed you have. Whereas speed, it just strips away, speed's a scalar, it just strips away all the directionality completely. You don't care about it. It's not part of it, right? So speed is a scalar, just a number, but velocity is magnitude, which is the speed, and its associated direction. So let's give a couple of quick examples. Let's say I have a ball here, and if you just forget what I've drawn on the board because I'm a terrible artist, it's called a ball, right? Nothing special. And let's say that I don't even draw an arrow anywhere. I don't even care. I just tell you that the speed of this ball is 10 meters per second. I have not drawn an arrow. You have no idea because I've taken a picture of this happening. If the ball is going this way, this way, this way, this way, this way, or into the board or out of the board, you have no idea, but you know that that's its speed at that moment in time. What are some examples of velocity? Well, here's a ball. Again, if you forget what I'm drawing here, there's a ball. And associated with this, now I tell you that this ball is traveling here with some velocity, and now I'm going to put an arrow on top of the velocity because I want to remind myself that this velocity is a vector. It has a direction. That's why we put an arrow on the top. All right? But along with knowing this, the length of this arrow telling me its magnitude, I also need to know which direction it's going. How do I define the direction? Well, what I do is just like in math class, I draw a little horizontal line and I call this angle theta. Now don't get scared about angle theta. Angle theta is just a number. It's how many degrees, or if you're in a trig class, you call it radians, but it's just measuring the angle. It's measuring the direction relative to a horizontal reference point, right? So then, if I tell you that this velocity vector is 10 meters per second, that is not sufficient because I haven't told you the direction. So I have to tell you at an angle theta of 27 degrees. From what? From however I've drawn it in my figure, from the local horizontal. You can think of this as like an x-axis right here. If you want to draw a coordinate system, this could be like an x-axis right here. So that's one example. But I want to drill this home because this is absolutely critical to understanding the difference between velocity and speed. Let's say that I draw this situation again, right? Let's say I draw this situation again. Actually, I'm going to squeeze it in. I'm going to squeeze it in a little bit tighter. Let's draw it up here. So that's a ball, same as always. But now this ball is traveling in this direction. Notice I've made the arrow about the same size as this one. I tried to. I'm going to put my little velocity marking telling you it's going that way. All right? Now I have to measure, in order to specify the velocity, I have to measure what direction it's traveling with respect to. So I have the same reference line that I had here, but now my angle is much bigger. See, this is a small angle, 27 degrees. Think about it this way. This is 90 degrees. Halfway is 45, a little bit less, that's 27. So if this is 90 degrees and this has to be bigger, let's just say that that's like 105 degrees or something like that. So what I can do is specify this velocity and say the velocity is, again, 10 meters per second, but the angle theta is 105 degrees. Now, what have we learned from this? These two vectors, put a little arrow here, these are different vectors. You see what I mean? I've drawn the length of this arrow the same as this one. The length of the arrow in a vector tells you how the magnitude is, how long the magnitude is. In other words, more meters per second, longer arrow. Shorter meters per second, shorter arrow. But the direction of it tells you which direction it's going. Now, because they're both traveling at 10 meters per second, the lengths of the arrows are the same. So most people would say they're doing the same thing, but they're not. This one's moving this way, and this one's moving this way. And because velocity is a vector, these are different. So even though they're both traveling at 10 meters per second, the velocity vectors are different because direction matters. Not just how fast it's moving, direction matters. That's critically important, okay? Let me draw one more quick example. It'll just take a second. And what we'll do is we'll draw another ball down here, just in case you forget. And what I'll try to do is draw the same angle as my original case, but I'm going to draw a shorter arrow. We'll call this vector V. And I'm going to do a dotted line here. This is angle theta. All right, what could this vector V be? Well, let's say that the velocity vector here, instead of, it can't be 10 meters per second because the arrow is shorter. It has to be a less of a speed, right? So let's say that this thing is, I don't know, this is about this big, that's about half of it. So we could say this is like 5 meters per second. And since I tried to draw this at the same angle as the original one, let's use the same angle here at an angle of 27 degrees. Let me ask you a question. Is this vector the same as this one? No, it's not the same. You see, the angles are the same in these cases. I tried to draw them the same. But the actual speed that's happening in both locations are different. So this vector is different than this one. This one is very clearly different than this one, and this one's different than this one as well. Why did I spend time drawing 3 different vectors of velocity? Because I want to drill it in your head that a vector has a magnitude, a length, and we represent it as the length of the arrow. That's its magnitude, but it also has its direction. And in order for 2 vectors to be the same, like equal to each other, they have to have the same length and the same direction. Both have to be the same because they're combinations of magnitude and direction. That's why these are all different, because something is different. Here, the 2 magnitudes are the same, but the directions are different. And over here, the 2 directions are the same, but the magnitudes are totally different. So now, we want to talk about how to calculate velocity. You see, we've given lots of examples. How do you calculate it? Well, you already sort of know how to calculate speed, right? You know that when you're traveling down the road at 10 meters per second, it means that you've gone 10 meters in 1 second. The slash in the unit, meters per second, it means division. It means how far did you travel divided by or compared to how long did it take. So 10 meters in 1 second is the same as 20 meters in 2 seconds. Think about it. If I travel 20 meters in 2 seconds, 20 divided by 2 is 10 meters per second. 10 divided by 1 is 10 meters per second. So it's the same velocity, whether I go, or the same speed, whether I go 10 meters in 1 second, 20 meters in 2 seconds. So you're just taking the distance traveled divided by the time. That gives you what we call the average speed. And the average, if you know the direction, it's the average velocity. But to drill down a little bit deeper in the details here, we have to take a break from velocity and speed just for a second. It's an important detour, I promise you. We have to talk about the difference between the distance of something and the displacement of something. And I'm going to promise you that we need to do that, but it's very simple to understand. Let's go to a fresh board. And we're going to talk about the difference between distance and displacement. Let's say that I'm starting a journey. So I'm going to start here. Here's my starting point. And my finishing line is here. So I'm going to say end. All right, now, how many different ways can I get from the starting point to the ending point? Well, I think you're smart enough to know that there's an infinite number of ways to get from the starting point to the ending point. I could go straight line. I mean, that would be the smart way to do it, right? But I could instead go here and then over there, or I could go here and then there, or I can go here and then back and then here and then back and then up there. Or instead of going that way, I can just go way down to the other end of the universe and then I can come back and then go there. You see, there's an infinite number of ways to go from start to end, right? Let's just draw one particular path. Let's say I first start by going up here. I'm going to put a little arrow this way. And then I turn and say, oh, I need to be going this way. And I'm not traveling in straight lines. That's why I've kind of had my wavy lines here. And let's say that this leg of the journey right here was 34 meters. And this leg of the journey up here was 20 meters. All right, so if I tell you that I actually took this path and I ask you what is the distance traveled, then you would answer that the distance, right, has to be the sum of these things, 34 plus 20, and I don't even need to write that down. You know that that's going to be 54 meters, right? Because distance is a scalar. Because you see, notice that I didn't really care which direction I went. I went up for one part of the distance, and then I went over for the other part of the distance, but I never really calculated the direction of anything when I calculated the distance. I just added one number and another number. They're totally different directions. I didn't include the direction of my walking anywhere in that calculation. That's why the distance along the path, it's just a scalar, it's just a number. Remember, like speed is just a number, or energy is just a number, or temperature is just a number. Distance traveled is just a number along the path. I don't care which way I go. The distance doesn't matter. I didn't take into account 34, I didn't look at the angle or anything like that. Now, what if I do take into account the angle or the direction involved? Then I wouldn't really care if I'm going up and over or not. All I would care about if I was really looking at the taking into account the distance or the direction is I would only care about the starting point and the ending point. So I'm going to draw a purple arrow here. The starting point directly to the ending point, that is what we call displacement. Right? Displacement is another word that you think it means the same thing as distance, but it doesn't. Displacement is basically the distance traveled, but only in a direct line from the starting point to the ending point. Think about it. If I tell you that the starting point is here and the ending point is here, and then I tell you, okay, close your eyes. And you close your eyes, and then I go all over the place, and then I end up here, and I say, okay, open your eyes. All you saw is I started here, and I ended here. That's its displacement. I don't care if this finger went all the way to the grocery store and over there, it just ended up in the same ending point. So whenever we have a situation where we have a starting point and an ending point, and that's all I really care about, and I'm trying to figure out how fast it traveled between the starting point and the ending point, I don't care if it went all the way over here or all the way over here. The displacement is displacing the distance essentially from the starting point directly in a straight line to the finish, right? Now, in order to measure the displacement, I need to know how far it went between start and end, but I also need to know the angle, right? So what I could do is draw a local horizontal like this and say an angle is right here. So what I could say is I could say this is however many meters it was. I haven't mathematically figured all this stuff out as far as like making it trigonometrically correct, but I could say, for instance, that displacement is like, I don't know, like, 50, let's see, it's 54, we call it like 47 meters at an angle of like, 42 degrees. Something like that. We know that this distance has to be smaller than all this distance over here because you know how triangles work and it's roughly a triangle. But you see what I'm saying? The displacement is a totally different number than the distance. But now we have included an angle information because when we look at the starting point and the ending point, and that's all we care about the direction of travel from the starting point to the ending point. So distance is just how far did you go along a path, including any backtracking you do, right? But displacement, you don't care about any backtracking. All you care about is the starting point and the ending point. All right, so let's take this idea and let's run with it and do something a little bit closer to reality. Let's say that instead of start and end points like this, let's say that my starting point is here and my ending point is over here. And let's say that instead of doing a meandering wavy line path, actually I have a very straight path horizontal like this. And then I turn and I make a very straight path vertical. So it's a two-legged path, and actually also that I make this a 90-degree angle. So I walk east and then I turn north, 90 degrees north, and I go straight up north. Now you see we're starting to get into math because now we have a right triangle. Because I can connect the other side of this from start to end like this. Right? Right, so let's say that the path took you 4 meters going east, and then once you turned, it was 3 meters going up. Now, those of you that know math know that since it's a right triangle and the two legs are 3 and 4, I already know that the 3, 4, 5 triangle is a special right triangle. I picked those numbers on purpose because I know that the hypotenuse, the leg of this side, has to be 5 meters, right? So what I can do is I can just put 5 meters here. So how do we compare the distance and displacement in this situation? So what I can do is I can say, well, the distance, right, is 3 plus 4 is 7 meters. 3 plus 4 is 7. That's the distance of my actual path. But notice I didn't care if I was going east or north. I don't take it into account with any angles. I just add the number. So distance is a scalar. It is just a number, no distance or no direction, right? But then whenever I go over here and try to figure out what this displacement is, when I go and do this displacement, right, I know that the displacement only depends on the starting point and the ending point. The starting point and the ending point. So from here to here, it was a distance over that path of 5 meters. So I can put down that it was 5 meters. However, I need to include the direction somehow. And what does this form? This forms an angle with the local horizontal. So I can specify an angle here. And I already know from trigonometry that this angle is 36.87 degrees. So I can write down that the distance is just a number. It's a scalar. And it's a totally different number than the displacement, which is a vector. It's from the starting point to the ending point in a straight line path, but I have to specify the angle because it's a vector quantity. Now, for those of you curious, how did I know it was 36.87? This is not a math class, but the way you'd figure it out is because this is a right triangle. And we know that in a right triangle, the angle here, the tangent of any angle, of the angle here and the acute angle and the right triangle here, opposite of the 90-degree angle here, is going to be the opposite over the adjacent side. You learned that in math class. The opposite side is 3 and the adjacent side is 4. This is the definition of the tangent. So if I want to figure out what the angle is, I take the inverse tangent on both sides. So on the left, I'm going to have the angle theta, and on the right, I have to take the inverse tangent of 3/4. Okay? So in other words, this is like an equation, like any equation in math. I take the inverse tangent to undo this, and I get the angle back. If you put 3/4 in a calculator, that's 0.75. Take the inverse tangent, the calculator will tell you it's 36.87 degrees. But even if you don't know any of this tangent business, the point still stands of the concept of what I'm trying to tell you. Distance takes into account the entire path. Displacement doesn't care about the path, or doesn't care about the actual path taken, only the starting and the ending points, but you take into account the direction along that final direct straight line path there. So now we have to get to the end of the road here. We have to calculate speed and velocity. We have to calculate speed and velocity. So what I've mentioned over here is that speed is a scalar quantity, and velocity is a vector quantity. So what I want to do is I'm going to write down the equations for speed and velocity, and they're very, very similar, and they're very easy also. So what you could say is average speed over 2 points in your path is equal to the distance traveled over the time elapsed. Distance is units of meters, and time is unit of seconds, so I'm going to put these in brackets. When I put brackets, it means this is just the units. You take distance, you divide by time, you get the average speed, okay? So if this is the equation for average speed, what would average velocity be? What would average velocity be? Well, it's going to be the vector version of this, which means it has to be the displacement divided by the time elapsed. But notice the displacement is still measured in meters, and the time is in seconds, so the unit here is also in meters per second. So this is what you'll see in a physics book or a physical science book, right? The speed is distance divided by time, but the distance is defined to be the actual path taken. In this case, it would be 7 meters divided by the time elapsed. But the velocity is the displacement divided by the time. But the displacement is not this path. The displacement is the straight line path from start to finish, including any directionality associated with it. And so the velocity has the same units of speed, but the numbers can be different. And if there's any backtracking going on, the difference between speed and velocity will be more and more different because the velocity doesn't pay attention to any backtracking at all. It's just a straight line distance. So we talked about speed. We've talked about velocity. We need to wrap it up in a bow by doing a couple of quick calculations, but they're very, very simple. We're going to talk about one-dimensional motion. And so a minute ago, we had two-dimensional motion with the triangles and looking at the paths and things. Let's make it simpler. Talk about one-dimensional motion. What do I mean by that? I have a number line here. This is just like a number line from 4th grade, nothing fancy. Here is 0, and then we have +5, and then we have -5. So we have something below 0. You can think of this as a temperature scale with positive and negative values, okay? And what we're going to do is we're going to have a particle, my finger, that can travel, but only in this dimension, in one dimension. Either back or forth is still just one dimension. 2 dimensions would be if there was a y-axis there, and 3 dimensions would be a z-axis toward you. And the current theories of physics are that there could be even 11 dimensions or even more. That's another lecture for a different day, but basically the extra dimensions could be curled up into microscopic sizes, so we don't see them. We say we live in a 3-dimensional space. If you include time, that's a 4th dimension. There are likely very many additional dimensions beyond that. That's what current theories of physics are. So we're going to start at the beginning and say there's only one dimension of travel in this case. And this particle can only slide along this string, so to speak, like it's a bead riding along a string here. So let's say we have some motion. Now we start here. And what I'm going to do is I'm going to draw a path. But because I can only do the path on this one line, if I go back and forth, I'm going to be scribbling on top of myself the whole time. So to make it clear, what I'm going to do is say, well, I'm going to start going here. I'm going to go there. And then I'm going to go back here. And then I'm going to go, right there. And then I backtrack again. And then I'm going to go all the way over to here. And this is my finish. Now, it's important for you to note that this object can only travel in one dimension. So I'm drawing it up like this so you can see it, but really it's like it's going here, and it's going back, and then it's going this way, and then back, and then it's going this way. You see it's backtracking over its initial path, but I can't draw it like that because you won't see it. So I'm kind of zigzagging it up just so you can sort of see it, okay? Now let's calculate the speed and displacement in this situation, okay? The average speed is distance over time. We just talked about that. Right? The average speed is distance over time. But what is the distance traveled? Here's 1 unit, there's 2, 3, 4, 5, then 6, 7, 8, 9, then 10, then 11, 12, 13, 14. So that's 14 meters. And then the time, I didn't even tell you that this path takes let's say it takes a 2 second for this whole entire thing to happen. The elapsed time, in other words, over 2 seconds. And so 14 divided by 2 is 7 meters per second. That is the speed, the average speed. So average speed, 7 meters per second. Notice that whenever I did the backtracking, this way, this way, this way, this way, I didn't keep track of what direction the path was going. I didn't say, well, this is positive and this is negative. I counted basically more distance no matter which way the thing went. It's just the total distance traveled. So 1, 2, 3, 4, 5, then 6, 7, 8, 9, then 10, 11, 12, 13, 14. That's why 14 meters is up here. Now let's do the calculation again for velocity. So average velocity. All right, average velocity. That's equal to not the distance, but the displacement divided by the same time elapsed, right? So what do we figure out here? What is the displacement? So for the displacement, we don't care about any of this zigzagging stuff. We only care about the start and we only care about the finish. And so really the finish line, to figure out how far it traveled from start to finish, what you do is you take the finish line, which is at positive 6. You subtract the starting point, which is 0. Notice we only cared about the starting and finishing. But from the final position minus the initial position, and again, it took 2 seconds. So 6 over 2, the average velocity, and this is positive divided by positive. So I'm going to put a positive 3 meters per second. Now you might say, well, how is the direction accounted for here? Well, you see, because we took the final position and we subtracted the initial position and we got a positive number, it's sort of like the positive velocities are traveling to the right, and negative velocities will be going the other way, because this is the positive direction, this is the negative direction. So instead of an angle, which is how we kept track of it before, in one dimension, the sign keeps track of it. The positive sign means the direction of the velocity is happening to the right. So the speed, the average speed is 7 meters per second. We don't care at all about the direction of that, but the average velocity is only 3 meters per second, but we know it's traveling to the right. This is a vector quantity, magnitude and direction. This is a scalar quantity. All right, we're going to do one more, and I think we're going to call it a day for this lesson here. Let's say that we start here at the origin, and we go this way, and then this way, and then this way, and then all the way here, and we end up here. That's our path. Let's calculate the speed and velocity again. So the average speed, we already know it's the total distance divided by the time, and let me tell you how much time this took. The time, you might call it delta t. Delta just means the change in the time, so don't get scared by that. Delta t is 4 seconds. That's the elapsed time, basically. So this average speed is going to be how far did it go total? 1, 2, then 3, 4, then 5, 6, 7, 8. It traveled 8 meters, and it took 4 seconds. So the average speed is 2 meters per second. But again, I don't care about the direction of this thing. I didn't keep track of it when it went backwards. I didn't keep track of this is negative and this is positive. I just kept adding the numbers up. So the direction isn't even contained in this calculation. It's just 2 meters per second average, no matter what direction it's traveling at. All right, now let's calculate the same thing, but with the average velocity. That is the displacement divided by the time. But what you do for displacement, it's the final position like we did here, the final position minus the initial position, right? But the final position here is actually at a negative number. This is -2. This is -1, -2, -3, -4, and -5. So the final position is actually -2, right? And the initial position started at 0. So we have a final position here, an initial position here, and the elapsed time is again still 4 seconds. So when we do this calculation, what we get, -2 minus 0 is just -2, and then now we have a negative divided by a positive. And you know from algebra, or from pre-algebra, that negative divided by positive is still a negative, and we simplify that to 1/2. So the average velocity is -1/2 meters per second, because it's meters on top and seconds on the bottom. So what does this direction, what is the direction of this thing? The direction is contained in the negative sign, which means to the left. So you see, the first time we calculated the average velocity, we got a positive number. And since the number line had positive numbers to the right, the positive average velocity means we have a magnitude of 3 and a direction, which means traveling to the right. That's what that is. The second time we did it, we had a different final and starting point. And so what we got here is we have a magnitude of 1/2 meters per second, but the negative sign just tells us if it's going to the left. So in science, in physics, when you see negative and positive signs on numbers, do not stress out about it. The negative sign is just telling you the direction of what it's doing, right? Positive in general is going one direction on the number line or in the coordinate plane. Negative sign usually just goes the other direction. We could do the same thing with sea level. Sea level is the level of the ocean. Positive numbers are above sea level, but we could say negative numbers are below sea level. Don't stress out about it. That's just an application of negative numbers. So we have talked about speed. We have talked about velocity. We talked about vectors. We talked about scalars. We've talked about displacement. We've talked about distance. I think we covered it all. The only thing I want to leave you with here at the end is everything we calculated here is called an average speed or an average velocity. It's literally looking at the endpoints for the average velocity and figuring out what the average is. But the problem is, in all this zigzagging here, when you only look at the endpoints here that are far away, then you kind of lose the granularity of what's really happening here. What about a situation like a rocket launch? When a rocket launches, it starts off at 0 meters per second and then rapidly accelerates. We'll talk about acceleration soon. And it goes faster and faster and faster and faster. In other words, the velocity is always changing when the rocket goes up and up and up. So whereas average velocity is looking at the endpoints and calculating the average velocity across the motion, we can talk about instantaneous velocity, which would be the velocity at a specific moment. Inside your rocket, you have a display telling you how fast you're going at this second. And then at the next second, it's a little faster. And the next second's a little faster. And the next second's a little faster. That's your instantaneous velocity. And how do we do that in the real world? Well, what we do, the computer just calculates the average velocity over a really small period of time. How far did I go in a tiny little period of time? And that is very going to be close to my instantaneous velocity. And as I shrink the time window down, maybe the course velocity is over a 5-second interval, but if I look like at a nanosecond interval, then it's very close to my instantaneous velocity. And when you get to calculus, you learn how to handle true instantaneous velocity. And that's another lesson for another day. But for now, I just wanted to introduce you to the concept of how does speed and velocity work. When you first learn about this, you might say, well, that seems kind of boring, who cares? But actually, our theories of space and time and even of gravity are wrapped up in how these concepts work. So I wanted to introduce you to it, and then I'd like you to follow me on to our next lesson where we will continue exploring how the universe works together.